Class, Adam Ward here. Want to talk to you about a second example of using dimensional analysis. In this case, we're going to work through an example that includes flow through porous media. All right. So the problem setup looks something like this. Picture that we're looking at a cross-section of a pipe with a discharged Q flowing through it. In that pipe, you've got a porous media filter. What does that mean? Think in your head like a cigarette filter, for example, or a sponge that this fluid is going to flow through. It's got a dimension h in the direction of flow, a porosity represented by that script n or nu. And our objective is to find the dimensionless terms that describe this situation. As one hint to get us started, porosity itself is already unitless. So that's the fraction of a filter that is pore space. So porosity itself is already non-dimensionalized and ultimately could exist as its own pi term or pi group. Okay, so let's walk through our steps of problem solving. Prior to this video, you should have watched me do example 1, where I was very explicit in working through this. So we'll try and follow those same steps again. Listing all variables that are involved in the problem. So there was the pressure drop in units of pressure is a force per unit area, so pounds per square foot, for example. And of course, if you want to work in MLT units, which I'm going to for this problem, we're going to replace that force with mass multiplied by acceleration. And so I end up with units for a pressure drop of mass per length time squared. Discharge is a volume per time. The thickness of the filter H is a length. Density is mass per unit volume. And we've got our viscosity at the bottom. And porosity, which we agreed was already unitless on the previous slide. So that's steps number 1 and 2 already done. How many pi terms? Again, we take the number of variables, 6 in this case, minus the number of dimensions, 3. We have mass, length, and time. And that tells us that we have 3 pi terms that we're going to need to form. So knowing that we have 3 pi terms, we need to pick which will be our anchoring variables and which will be our repeating variables. And so just to remind us, this is the problem that we started with and the units in blue. So let's talk through the decision process of which will be anchoring and which will be repeating variables. If you are not forming a pi term or an anchor, then you are going to be a repeating variable. 6 variables minus 3 pi terms means 3 repeaters. So 3 anchors, 3 repeating variables. The left-hand side of that equation is always going to be an anchor. That's a given. So I'll circle the anchors in orange on this slide. As I said a few slides ago, porosity itself is already unitless. So I'm going to pick that for an anchor because, frankly, I'm lazy. There is no mass, length, or time that needs to be non-dimensionalized with a repeating variable, so porosity itself can be a pi term. I'm lazy, I'll pick it. And finally, I'm going to pick viscosity because it has the most complicated looking units to me, so I wrote looks complicated or looks complex. And I'm saying it looks complex because it has mass, length, and time, whereas the other variables only have 2 of those 3 dimensions. So that leaves me with 3 repeating variables. And just to confirm, we want those to include all of the dimensions. So mass, length, and time must show up in those 3 that I've circled in green. We want variables that look different from one another. So picking 2 variables that have the exact same units would not be a wise choice. And my personal preference is to use repeating variables that are simpler in terms of their units. That just makes the math easier in some of the future steps. So I'll argue that all 3 of those are met and we should proceed. Next step is to form a pi term. And so we'll always start, that pi 1 will start with what was on the left-hand side of the initial equation, that pressure drop, the thing that we're actually trying to predict. And so you can see what I've done is multiply that by each of our three repeating variables: discharge Q, thickness of filter H, and density of fluid rho. And those have been raised respectively to the A, B, and C powers. So now we're going to write this out with the fundamental units that go with each term. If you watched my example 1 video, you would have seen me use color to keep track of where these things came from. So I used different colors for pi 1, delta P, and Q, and so on. Here I thought I would change it up a little bit, and if that didn't work for you, now I'm trying to use these colors to represent the masses, the lengths, and the times, so that you can see where the M's, L's, and T's are actually coming from as we write this equation. So we've taken our equation and we've expressed it in terms of the mass, length, and time units associated with each term. So our next step then is going to be to write out separate equations for mass, length, and time. And so for mass, you can see that I'm going ahead and grabbing the units associated with mass from each of those equations. And I've added these hashed orange lines just to help you sort of see which variables or which terms are contributing here. So for mass, we have 0 on the left-hand side because we have a m0 to the left of the equal sign. Then in the first term on the right-hand side, we have a 1 because that's mass raised to the first power. The second term, we have 0 times a because there is no mass, so m to the 0 in that case. Second term, we similarly have 0b, and in the third term, we have 1c. That's going to be our strategy moving forward. So that was the mass equation. Similarly, you can write these out for length and time. So at this point, my hope is that these colors are helping you see where these exponents are coming from. We've got 3 equations with 3 unknowns. And so we can actually solve that system of equations. And I believe the solution is correct here. A is -2, B is 4, and C is -1, which means that our pi 1 term should look like this. So we have successfully formed our first pi term. Next step is to repeat that same process for the additional anchoring variables. So I'll work on viscosity next. You can see we've set it up the exact same way as we did in the previous problem. Again, we're going to go through and we're going to use the dimensions associated with each variable. And you can see now I'm not using color to help organize us. I'm just going to do everything in one color of ink. And our next step then is write out these 3 separate equations, one for mass, one for length, one for time. And again, I'll use those orange hashed lines just to help you see which terms of the equations are contributing. So there's our equation for mass, for length written in red, and for time written in green. And so importantly here, just to drive this home one last time, if a dimension doesn't exist, so for example, if we look at the term that I've pointed this pink arrow to, it only has a length scale in the dimensions, which means you get zeros in the equations that are not related to length scale. One other note to just point out here, you'll see where I'm circling in pink right now that I always use a plus sign in between my terms, and then I grab those minus signs and I actually write them in separately. And this is just so I don't confuse myself. I've got a habit of always writing the plus signs in between the terms and then putting those negative signs in. So that's something I do to try to help keep track of variables and which things should be added versus subtracted. Okay, 3 equations, 3 unknowns. We can go ahead and solve this, and I got A of -1, B of 1, and c of -1, which means my second pi term looks something like this. I've got mu multiplied by h on top, and in the denominator I've got fluid density multiplied by discharge. And as a final reminder, I won't show an explicit slide for pi 3. That last anchoring variable was porosity itself, nu. And if you work through this exact same process, what you'll find is that A, B, and C all have to equal 0 in that case. Because there's no dimensions to eliminate, you don't need any repeating variables. All right, so we've got our pi terms. Time to check our work. So here was that first pi term that we came up with. And you can see here that what I've done is write out the dimensions for each of the variables. So the first term, delta p. The second term is that h to the fourth. The third term, we have a q squared on the bottom. And so you can see that I've just sort of written out in the second line there, how did I think about 1 over q squared? Well, I thought about it as 1 over q quantity squared, or the dimensions on q, which is length cubed per time. So 1 over q is time per length cubed, squared. And then you can distribute that 2 back inside of the parentheses. So 2 times the exponent of 1 gives us a 2. 2 times the exponent of 3 gives us a 6. So that's where the units came from on my term for 1 over q squared. And then 1 over density would be that final term, which is apparently not written next, but I'll add it in. So that last term is 1 over density. So now we can go through and start to cancel. I've got a mass on the top and a mass on the bottom. I've got 2 times on the top and 2 times on the bottom. And I've got a total of 7 length scales on both the top and the bottom. So yes, pi 1 is dimensionless. You all should be able to repeat that for pi 2. And of course, pi 3 has been unitless since, the second slide in this lecture. So we feel good about our pi terms, having checked them. And the final step is to express the form of this relationship. So in its most generic sense, it's pi 1 equals some function of pi 2 and pi 3. And we'll go ahead and plug in the pi terms that we generated through this step. So what I've boxed here in red is what your final solution should look like for this problem. And we've gone from a relationship that had 6 terms in it, delta p equaled a function of 5 other things, to a relationship that has just 3 terms in it. This left-hand grouping equals some function phi of 2 groupings on the right-hand side. And so, yet again, Buckingham's pi theorem has taken a complicated problem and reduced that parameter space, or reduced the dimensionality of it to something that might be more tractable as we move forward with experiments or scale models. I've got one more example video that I'll post on this, and then we'll start our next lecture, which will be about similitude and modeling, or how we take advantage of this relationship. Thanks for sticking with me all, and I will see you in the next video. Have a good one.